Greetings. In this one, let's talk about planar graphs with no triangles, with no free cycles. We can devise or find out a nice inequality. And namely, we have to consider the fact that if it has no triangles, then every face in that graph, every face in that graph, adding the edges around the region, bounding a region, will be of length at least four edges. So let's denote f the number of faces and e the number of edges in the whole graph. And now we can find some interesting inequality first that would indirectly lead to the final inequality we want to look in this video. And that is that first of all, let's realize that 2 times the number of edges equals the sum of face lengths. All right, so how could we write this? Is, for example, sum of face lengths. So abstractly write it like this. So the length of a face is going to be 2 times the number of edges. Each edge bounds 2 faces on either of its sides, on both of its sides. And also we have that sum of face lengths, so this thing should be higher or equal to 4 times the number of faces. And that is because every face has length at least 4. So this length 1 here, 2e is higher or equal than 4 times f. So e is higher or equal to 2f. And let's also now make use of the Euler's formula regarding the number of edges, vertices, and faces in a planar graph. And that namely says v minus e plus f equals 2. And we can take out, because what we in the end want to get is the relationship between the number of vertices and the number of edges, and namely the maximum number of edges in a triangle-free planar graph. So if we want to get that, now it's important to integrate this equation in this inequality. So what that says is we can take out what f means. So f is 2 plus e minus v. And this f I can put in the e is higher or equal to 2f. So e is higher or equal to 2 times 2 plus e minus v. And that is e is higher or equal to 4 plus 2e minus 2v. And I would subtract e from both sides and add 2v and subtract 4. So 2v minus 4 is higher or equal to e. And this is a very neat result now, because this result is basically what we were looking for. Of course, we consider it for n higher than 3 because we're talking of triangle-free. Triangle has 3 edges and 3 vertices as a graph on its own, right? If we look at a triangle on its own. So it makes sense to consider n higher or equal to 3, by the way. So that's a thing to note. But anyway, we now have this very useful inequality that solves a lot of questions. It, for example, tells us the maximum number of edges that a graph can have in order for it to have not a triangle and be planar. We can check it, for example, for some path. So if we have 3 vertices and 2 edges, of course it will work. That is 2 edges smaller or equal to 3 times 2 minus 4. Well, 2 equals 2. So that's still satisfied. We can also take some arbitrarily large cycle that is higher than, actually, that is not a free cycle of length 3. So for example, this is 1, 2, 3, 4, 5, 6. So this is C6. So let's see. Well, we would have, again, 2v minus 4 is higher or equal than e. 2v minus 4 satisfies this. Well, we have 12 minus 4 is bigger than, again, also 6 edges here. So that works out. 8 is more than 6. So that's useful. And let's now delete this and consider one more thing. And namely, let's consider k free free. So if we have k free free It is a bipartite graph, complete one. That means from one side we connect each vertex to all the vertices on the other side. We draw the graph like this. All right. So the way we choose to draw it here is, of course, somehow arbitrary, but this is like the more default way to draw bipartite graphs, to show that the vertices on either side, or both of the two sides, are not connected to each other, but they're connected to the vertices on the other side. And this is complete case. So it means each of the three vertices on the left side connected to all the three vertices on the right side. And the same applies from the right side to the left side. So now we have that. So case sub 3, and now is it planar? It's not. So not planar, okay, because we have a condition that's right here that says if you have a graph that's planar and it has no triangles, no free cycles, then the number of edges must be maximally 2v minus 4. And this, let's suppose it's a planar graph and it does not have triangles. We see it doesn't have triangles because a bipartite graph does not. It comes from the nature of how we can draw it like this. We connect it to the vertices of the other side, but we don't connect the vertices among themselves on the left side, the three of them on the left side and the three of them on the right side. So we can directly apply this formula, count the number of edges. So that would be 9, because 3 vertices on the left side connected to 3 vertices on the right side each. It's k3. It's 3 times 3, number of edges. Number of vertices will be number of vertices is easily counted. We count the vertices directly. So we see there is 6 of them. So we have v equaling 6. So by the inequality above, we have 12 right here. 12 minus 4 bigger than 9. And that doesn't apply. So this graph is not planar. So that could be also used for proving such a statement.